Testing, testing. Góðan daginn, ég heiti Haukur Ingi og býð ykkur velkomin á ráðstefnu loftslagsbreytingar á norðurslóðum. Ég og kona mín Berglind eigum okkur draum að koma á fót jökla og fjallasetri hér á Halaði Suðursveit sem eru við rætur Jökulsárlóns þar sem áhrif loftslagsbreytinga eru hvað sýnilegastar. Með setrinu viljum við meðal annars byggja brýr á milli samfélags, vísindamanna og almennings, búa til tækifæri fyrir einstaklinga til að skiptast á skoðunum og mynda tengsl sem annars hefðu ekki verið möguleg. Þannig viljum við leggja okkar að mörkum við að finna og þróa leið að sjálfbærni til framtíðar. Brátt munum við hlusta á erindi breytingar á jöklum, náttúru og samfélagi sem eiga sér stað nú í þessum töluðu orðum. Það sem við erum með marga erlenda hlustendur munum við nú skipta yfir á ensku. So, welcome to this conference about sustainability and climate change in the Arctic. My name is Haukur Ingi, and with my wife, Berglind, we have a dream to establish a glacier and mountain center here in Hali in Suðursveit, which is at the root of Lagoon Jökulsárlón, where climate changes are appearing in the most dramatic way. With the center, we would like to build bridges between the science world and the normal world, create opportunities for individuals to interact, communicate, and establish relationships that they otherwise would not have had the opportunity to do. Among other things, we would like to contribute to our local society and the world itself, helping to create a path to sustainability for future generations. Soon you will listen to presentations about changes on glaciers, nature, communities, which is happening as we speak. The agenda is as follows. 10 students will host their presentation, each lasting 10 minutes, including questions. So please write them down and post them on the chat on YouTube or ask from your seats. The students will answer them after their presentations or at the end of the conference. We will have the students do their presentation in 4 slots, having 3 presentations and then 2 10-minute break plus 1 2-minute break to set up the last presentation, which is a video presentation. In the end of the conference, we will move to questions and answers. Now, I would like to welcome Owen Bailey from Bates College to start his presentation. So Owen, welcome.
Hi there. I'd like to start by thanking everyone for coming today, both in person and online, and by thanking Heuker for donating his space and his time to this event today. It's a great thing to share what we've learned in our limited time here with those who actually live here. A little bit about me. I'm an undergraduate chemistry student at Bates College, and today I'll be presenting my short study on trace metals in the environment, focused on Breidamörkjökull's glacial lagoon, Jökulsárlón. First, I'd like to talk about how glaciers in Iceland form. As snow falls year after year, layers are created, as shown in the figure. Each layer is from 1 year of snow. As these layers build up over the years, their weight begins to apply a huge downward pressure throughout the glacial body. This downward pressure eventually gathers enough to push itself forward. Glaciers are defined as bodies of ice and snow capable of moving under their own weight. In Iceland, however, this process is affected by other natural processes, like volcanic systems. During a volcanic eruption, ash and volcanic debris are deposited on top of the most recent layer of glacial ice and snow. This layer of ash and debris settles on the surface of the glacier, insulating the layers beneath. After the eruption, snowfall continues and the layer building process resumes. Layers continue to build up, burying the stripe of dark volcanic debris in the body of the glacier. Over the years, more volcanic eruptions occur, layering more debris and ash, perhaps of a different composition, on top of the glacier, to then be covered with more snow and ice. This process continues for hundreds of years, leaving Iceland's glaciers with very clearly stratified ice and ash layers. I took this picture on Breidamörkjökull a few weeks ago. At that spot, I guess you can't see in the light. But. Now let's look at Breidamörkjökull in particular. When the glacier melts into its lagoon, Jökulsárlón, it deposits the ash into the water there. These plumes are visible in satellite imagery. You can see the arrow pointing to the ash. Due to climate change, the melting process is speeding up. This means that as the planet warms, the rate of ash deposition from glaciers into their respective lagoons will increase. Now, why does this matter? Importantly, each volcanic eruption contains deep earth, heavy metals that are often harmful to ecosystems. These are locked up in the glacier until they melt out into their lagoons. I set out to answer some questions about these trace metals. Specifically, I wanted to find out whether the distance to the mouth of the lagoon had any effect on trace metal concentration, in order to discern whether or not trace metal introduction to the coastal ecosystems might be impactful. I chose 6 sample sites, A through F, 500 meters apart from one another, and with 6 replicates at each site. In gathering data, I took water samples, pH, temperature, and GPS coordinates in Jökulsárlón. That's me in the lagoon there. When studying trace metals, it's important to have very clean equipment, to have proper procedures, and proper storage. With the help of Sean Scully and Eva Maria Ingvadóttir at the University of Akureyri, I put my sampling bottles through an acid bath for 25 hours to remove any contaminants before sampling. I also sampled with nitrile gloves on. After collection, I stored my samples in a cold, dark environment. I then traveled with them to the Marine and Freshwater Research Institute in Hafnarfjörður, where, with help from Solveig Rosa Ólafsdóttir, I filtered and acid-treated the samples to prepare for shipment. With the help of Heuker, the samples were then shipped off to a lab in the States. Unfortunately, the samples have only just arrived in the States and have not been analyzed, so I don't have any data to present from this part of the study. However, I have conducted a literature analysis connecting environmental parameters to trace metals. For this analysis, I looked at data from a previous study which analyzed trace metal concentrations in Jökulsárlón from 2015. This study found high concentrations of all studied trace metals. Importantly, elevated iron concentrations are of note. On the left, I've inserted the EC20 guidelines for these metals. The EC20 benchmark displays the lowest concentration of each metal, which will decrease female reproductive output of daphnids on the left and fish on the right by 20%, an important benchmark for ecosystems. While most metal concentrations are lower than the EC20 guidelines, bioaccumulation up the food chain remains an issue. From here on, we will follow cadmium, the second from the left, as its environmental impact is widely studied. This is a very simplified food web for the Icelandic coastal marine wildlife. The food web is controlled by high primary production of capelin and is based in its lowest levels on phyto and zooplankton species. These two species take up about 80% of the dissolved cadmium in the water. As previously mentioned, bioaccumulation occurs greatly in marine food chains. Phytoplankton and zooplankton take up the dissolved cadmium and are subsequently eaten by herring and capelin, which then store the cadmium concentration in their own bodies. Capelin's importance in Iceland can't be understated. Cod is an important staple both here and for export elsewhere. When we eat these fish, we then intake the gathered cadmium, which then affects our own health. The last piece of the puzzle concerned the behavior of these metals in different conditions. My initial aim was to observe a relationship between environmental parameters and concentration of trace metals. I thus decided to base the literature analysis off of the parameters in Jökulsárlón. In the first figure, applying the collected pH value of around 8.25, that red line, we can observe a significant difference between the dissolved concentration of cadmium in salt water versus fresh water. This paper convincingly found that cadmium will desorb from the suspended particulate matter into the dissolved phase at greater rates in salt water than in fresh water at this pH. Another study found that as salinity increases, the dissolved concentration of cadmium does as well. Both of these studies demonstrate the environmental impacts that can affect how much cadmium is available for uptake by marine organisms, as one example of many ash source trace metals. My last step was to apply this information to Iceland's glacial lagoons, many of which have equal or even higher concentrations of trace metals from ash deposition, which will only increase as the glaciers melt over time. Since we have found that increased salinity leads to higher dissolved concentration of cadmium, thus higher availability of the metal for uptake, we can now look at how these glacial lagoons eventually flood into the saline coastal ecosystems. The entrance of trace metals into saline marine ecosystems could have drastic effects on the food web, including trophic mismatch, further destabilization of the food web, including lower reproductive rates, and increased bioaccumulation, leading directly to our own health. I'd like to thank all the people who have helped me greatly through these 5 weeks, namely Dewi for her help sampling, Dan Gavoni for his academic advice, and Hauker for helping me logistically and providing us all with a guidance and a fantastic place to study. Thank you. Any questions? Yeah. I know some things are not quite finished. Yes. But really, really well done. Thank you. Thank you very much. One question. Yeah. Is there also research done after how many of these cadmium is taken up by fish here in the lagoon? Not. Oh. So the question was, is there research being done in Jökulsárlón on how cadmium is being taken up by marine wildlife in the lagoon itself? I'm not actually sure about specifically Jökulsárlón, but there is extensive research on ecosystems uptake of cadmium itself. I'm just not entirely sure about Jökulsárlón. If that answers the question. Any others? Okay, thank you.
Thank you, Owen, for this presentation. So next one is Celine Noor-Smith from Charlton College, Northfield. Welcome, Celine.
Hi, my name is Celine Smith, and I'm a geology student at Carleton College in Minnesota. And today I'll be talking about a potentially unstable slope on Mývatnstinder, and that's the eastern slope surrounding Fjallsjökull, and that's the outlet glacier of Vatnajökull. So a little background on why this is important and why it's related to climate change. So with anthropogenic sources of CO2, the climate has been warming. Just do the laser. So here's a graph from the IPCC AR5, and we can see that in every scenario, there's an increase in temperature. So that means glaciers that are currently retreating will continue to retreat, and then permafrost will also continue to thaw. So this has implications for landslides because of something called debuttressing. So as glaciers are formed, they carve really steep slopes, and then as the ice retreats, those slopes are left behind, and because they're so steep and there's no more ice to support the slope, that causes landslides potential. So the exact mechanism of debuttressing is disputed, but it's generally accepted that as glaciers will continue to retreat and as permafrost thaws, there will be more landslides. So my research came about when I contacted Daniel Ben Yehoshua, who's my advisor. He's a PhD student at the University of Iceland and has also worked for the drone sensing company Svarmi. So I asked him about landslides and glaciers, and he told me about this current flake that he saw by looking at satellite imagery. So here's a time series. We have a picture from 2003, 2015, and 2019. And we can see here that a crack is starting to form. And we can see in 2019 that crack has very much enlarged. And these are images from map.is. So a little bit before I go into my research question, I'll talk about Fjalsjökull's recession rate. So it's been steadily retreating since the Little Ice Age, and also steadily thinning, and the proglacial lake at the end, so Fjalsárlón, has also been increasing in area. So because Miðafstrandstindur over here has lost its buttressing, I was wondering how the stability might change. And because of landslides, it's pressing that we do a slope stability analysis. So this brings me to my question of how much of a landslide risk does the detaching flake on Miðafstrandstindur pose through measurements of length, width, and dip angle by making a DEM, so a digital elevation model. And here's a drone picture that we took, and here is the flake and the crack. Now I'll speak a little bit about my methodology, but before that I'll just show the study site and the area of interest. So here we have a map of Iceland and Vatnajökull, and then an inlay of Fjalsjökull and the lagoon, and then here is the area of interest in the flake, circled in yellow. So my methodology was that we hiked up to the terminal moraine of Fjalsjökull, and this was, I was accompanied by Mike Reed, who is a glacier guide at Glacier Adventure, and he was very helpful, and he flew the drone as well. So we hiked up to the terminal moraine, launched the DJI Mavic Pro drone, flew it to the slope, took some overlapping pictures for a DEM, and then my advisor uploaded them into Pix4D and created a point cloud and a 3D mesh, and then I imported that DEM into Cloud Compare and took some measurements. So here are my results, and this is the 3D mesh that was imported into Cloud Compare. So what I found was that there was one main primary crack, and that's the one in blue here, 7 smaller secondary cracks, and also that 72.8% of the main crack had a significant width, so 72% of it wasn't filled in by rubble and was actively detaching. Here is a better image of it. We see the cracks that are labeled over here with the length in meters. So the primary crack was around 300 meters in length, and then the second is 35 meters in length, and that's over here. And this will become a little more significant later on. This is a figure showing the areas that aren't actively detaching, so these are just areas that I thought might be interesting because they were filled in with rubble. And that was 27% of the crack was filled in with that kind of rubble, and they're highlighted in pink over here. One area was detaching much more than the rest, and I thought I might take separate measurements of that single area. So here, these green lines are done on Cloud Compare, and they're just width measurements. So for the full primary crack, the average width was around 3.7 meters. The minimum was 1.19, and the maximum was 9.5 meters, and that is this measurement right here, somewhere around here. And then for this widest section of the crack, I thought it would be interesting to do separate ones. So the average of width for this section. And this is also where a secondary crack B, the largest one, is. And then the minimum is 3.59 meters. And then finally, I did a strike and dip measurement. So I did this by fitting a plane in Cloud Compare to the crack and then measuring the strike and dip from that plane to try to estimate the strike and dip of the crack. So the dip direction was southeast, the strike was 78 azimuth, and then the dip from horizontal is around 80 degrees, which is quite steep. So now, what does this all mean and why does it matter? So the measurements are concerning enough to monitor because they're quite similar to the Fisher and Svinefjellsheiði, which is meters in length and 60 million cubic meters in volume. So the length and dip of the one that I measured is slightly similar, and I think it's concerning enough to monitor and to keep track of it. And then the secondary cracks that I found might indicate that there's a potentially larger, and then the area with the widest crack, so those the 9.5 meter width, will likely slide first and could be a catalyst for larger movement. So that could create a domino effect and have a larger slide. So this requires a lot of further study. Ideally, I would do a measurement volume, but because of the time limit, measurement volume, because of the time limit, it was quite hard. But yes, as long as the data is out there, that it can be done later on. And then ideally, we'd also have rates of crack increase and decrease over time. And then from a volume estimate, you can get a mass estimate. So this slide might be severe because Fjallsjökull is floating on the lagoon, and it's quite thin. Here are some ice thickness measurements from 2012, so it's likely thinner now, but it's around 40 at the terminus and then around 100 meters where the area of interest is. So this could cause a displacement wave and a calving event, but it could also not, so that's why it needs some further monitoring. And then so to conclude, the flake of land is worth closely monitoring. The current crack length is, the widest crack length is 9.5 meters, and then this could possibly cause a calving event or a tidal wave, a small one. But and then I'd like to thank Hauker for accommodating our stay here and facilitating our field work and being very, very helpful, and also Mike Reed for helping with the data and the drone pictures, and then my advisor for helping me with some guidance and doing the DEM for me. So, thank you. Questions? Yeah, weather usually the question was how ordering this crack later on. So there's weather that monitors Svinefjellsheiði, and they do some yearly estimates, and maybe not yearly, even more than yearly, but they have ways to monitor it and take rate measurements.
Yes, thank you very much.
Thank you.
I think, although this is a well-known phenomenon, side effect of glacial melting, I think we really haven't become very conscious of this in Iceland until Svinefjellsheiði.
Mm-hmm.
But what I was interested in, you mentioned that you found this area because of some drone work your supervisor has been doing. Understood that. Could you tell me a bit more about that? Because I'm very interested in visual research, and it seems to be like a prime example.
Yeah. The initial flake was found. Is that it? So he was looking at just satellite imagery on map.is because that's his PhD work is looking at Svinefjellsheiði. So he oftentimes, I guess, will look at satellite imagery and just notice this change over time. Yeah. Thank you so much.
Thank you. And next one up is Laila Ronsinski from the University of California, Santa Cruz. Laila, welcome. Coming out of the midget door, yeah?
Hi everyone. Thank you so much. So my name is Lila Roginski. I'm from UC Santa Cruz with the program SIT, and I tested the 10 largest lichen approach on the Breda-Merkiokul foreland. So my research questions included: is the 10 largest lichen approach a viable method for dating the glacial retreat of Breda-Merkiokul? And how can lichen population dynamics within glacial foreground help us the world's glaciers? So an overview of lichenometry. So why is it used? It's used to date century-old surfaces and geomorphic processes. It aids in the understanding of global warming into the climatic systems that have molded the surface of the Earth. And since the last little ice age maximum, the following period of historical climate change and glacial recession has been very well documented by lichenomic techniques. So, lichens are a symbiotic fungi that grow on rocks, trees, and man-made surfaces, and by measuring their researchers can approximate the date of deposition on a surface within the last 500 years. For lichenometric methods to work, two constants must be known, and that is the lag time between before colonization of a surface and the growth rate of the lichen species. I used the largest lichen approach because it is inexpensive, quick, and relatively accurate. It's also a very common lichenometric approach, and it's relatively simple. It exists under the premise that the largest thallus, being the first to colonize a surface, coincides with the minimum age of the surface, which would be closest to its actual age. Okay, here in figure 1, it's indicated by the red star at the foot of Breda-Merkiokul, and then on the right, my moraine sequences are shown through a GIS-generated map given to me by Snævar. Thank you, Snævar. So my methods. So here I used the map as well as satellite imagery to locate my moraine ridges, and there are 6 of them, which each had an area of around 1,000 meters squared. I measured the lichen species. They're commonly found in Iceland, especially on glacial forelands, and they have a relatively stable growth rate, which makes them good for lichenometric studies. I measured the 10 largest at each site, beginning with the first moraine, and by doing this I walked along the ridge of the moraine and used a plastic ruler measuring its longest axis. A total of 60 thallus measurements were taken, and the average of 10 from each site was used for the statistical analysis. So I used a one-way ANOVA test. The assumption of equal variance and normality was met by visual assessment of the residuals versus fitted plot, and the Tukey's HSD test determined specific differences between the sites under an alpha of 0.05. And then a box plot was created in R. So I hypothesized that there would be a positive correlation between lichen size and time since deglaciation of a surface, and that this positive correlation would be a result of lichen population dynamics as they react to factors such as environmental conditions, nutrient availability, and time for colonization. Here are my testing fields. So moraine 1 is located at the very bottom, furthest from the glacier. The glacier is at the top. Moraine 1 was deglaciated in 1880, and then all the way up to M6, which was deglaciated in 1955. This is the box plot that was created in R. So These are the lichen diameters at the 6 different study sites. So the moraines are shown on the x-axis and diameter is shown on the y. So the black bar in the middle is the median diameter. And then the letters on the top indicate which sites were significantly different from each other. So M1 and M2 were similar but significantly different. You can see the same with M3, M4, and M5. They were all similar to each other but different from M1, M2, and M6. This then shows us that there was statistical significance in the data. So that is exciting news. So discussing these results, a key reason for this time gradient growth pattern of the lichen is the nutrient availability, substrate availability, and the time for colonization. My hypothesis that there would be a lichen radial increase with time since deglaciation was largely proven by the results of the study. And this is shown through the significant difference between the moraine sites. Yes, so there was a chronological to the foreland represented by. Okay, so the one anomalous pattern that we saw in the data was between moraines 3 and 4. The average radial development of the lichens at M3 was smaller than at M4, which is not what I hypothesized. M3 was deglaciated in 1930 and M4 in 1945. However, M3 had a smaller radial development of lichen than M4 by 3.6 millimeters. This difference was not statistically significant. However, it's to look at for reasons why. So one explanation would be a high mortality rate among the first lichens to colonize the surface of M3. M3 actually contained an outlier at the top there that you can see right in the middle. And there's a high variety of measurements ranging from as low as 35 millimeters to a maximum of 65, meaning that there may have been high mortality in the first colonizers. Explanation would be environmental change. This is likely because terrain located near Icelandic glaciers is highly susceptible to intense weather patterns. Its close proximity to Vatnajökull, the largest ice cap in Europe, and North Pole and North Atlantic Ocean are all reasons for high environmental variability, which would affect the growth rate of the lichens. Another explanation would be human interference. The massive amount of tourism that Iceland has experienced in the past decade has had a substantial impact on the environment, especially near rare attractions such as glaciers. So the foot traffic of tourists as well as scientists may affect the lichen's growth rate. Not the rate, the lichen's growth over time. Okay, and then a final explanation would be a weakness with the largest lichen method found with the LL technique. Because it only takes into account the largest thalli, the proposed average result neglects anomalously large lichen in the data. So there is a low statistical significance due to the small amount of measurements. As well as individual lichen fused together as seen in this photo, making it difficult to know if it's a single thallus or a combination of a lot. So, in conclusion, the 10 largest lichen approach did prove to be a valuable tool in dating the glacial retreat of Breiðamerkurjökull, and analyzing the lichen population dynamics of deglaciated moraine surfaces was useful in understanding the rate of retreat, and this could be translated to the world's glaciers as well. So the long-term and far-reaching consequences of melting glaciers, there are many listed here and more. Sea level rise, coastal erosion, storm surges, damage to the agriculture sector, damage to animals and wildlife. Lichenometry can help us understand all of these potential negative impacts. these are my acknowledgements. Thank you to everyone here, and my citations. Any questions? Thank you. Well, my research actually didn't go into the landform specifically, but I do acknowledge all the problems that are associated with ligonometry. Um, the landforms could definitely play a part in the anomaly, and I'd love to look into that more, but I didn't find anything like that in my research. Thank you, though.
So, Laila, thank you for. Oh, sorry. So now we will take a 10 minutes break, and we'll come back after 10 minutes. And some of you might be struggling with our live streaming, but we are going to look into that now and into the break. Thank you. Yes, I will introduce you. So next one on is Talia Elman, and yeah, there you go. Welcome.
Hi everyone, my name is Tali Emlyn and I am an undergraduate geology student at Carleton College. Today I'll be talking to you about a 5-week study I did on climate and its impact on the growth of the common juniper in Iceland. I conducted this study along with Olafur Eggertsson of the Icelandic Forest Service. The common juniper is a very widespread conifer, and it's found mainly in the northern temperate zone. And it is one of many shrub species that is moving north due to climate change favoring growth in previously inhospitable environments. So the impact of all of these Arctic shrubs moving north can be changes in the permafrost active layer, changes in albedo, and changes in soil fertility, specifically for the juniper in nitrogen and phosphorus availability. So we know that the juniper is moving north and expanding its range. However, it is unclear exactly what climate influences have on the growth. Additionally, there are no found published papers on juniper growth in Iceland. So our question was, how does climate influence the growth of the common juniper in southwest Iceland, specifically in the Reykjanes region? So we used dendrochronology as a helpful tool to look at how growth rate is changing over time annually. Past studies on juniper growth have shown that temperature rather than precipitation has influence on growth, and we decided to look in this subarctic region. So we collected samples in the Reykjanes region. Olafur, along with some students, collected samples in June 2019, and then we collected more samples in November 2020. And we used annual ring widths and compared them to summer climate variables in order to assess growth. Samples are prepared in the lab by cutting them and polishing and observing them under the microscope. Each ring width was measured in micrometers and uploaded into a program for further analysis. So we used 2 different programs to index the data, and the indexing, it helps to flatten out the chronology, so it takes out any influence of things like sheep grazing or natural increases of growth with age. Additionally, we used the program CoFetcha, which is used for cross-dating and creation of a residual model. So it compares all of our samples and makes sure that we're not missing any rings so that we can get an accurate chronology. And the program TSAP-WIN was used for indexation and creation of a master chronology. What we found. Climate in the Reykjanes region is changing. So as you can see, the summer average temperature for the past 40 years has been steadily increasing, and this is expected to continue. However, there have been no significant changes in summer precipitation. And we chose to look specifically in the summer because that is the growing season in Iceland. So that means June, July, and August. This is the indexed chronology that was created by Olafur Eggertsson. And as you can see, there are annual fluctuations in the growth. So here we're comparing summer average temperature with growth. So there is a weak positive relationship between average temperature and growth. So as summers continue to warm, growth rate also increases. There was no significant relationship between summer precipitation and growth, so amount of precipitation does not have an influence. So after looking at these general trends, we decided to go back and look at individual summer months and found that For the month of August, summer temperatures had a positive relationship with growth, whereas no other month had a significant impact. So as you can see to the right, there is a positive correlation between August temperature and growth. So what this all means is that as summers continue to warm, we can expect an increased growth rate of the common juniper in southwest Iceland. And we know from our data that the precipitation had no influence. So this has a lot of implications for ground cover in the Arctic. This can impact carbon storage and permafrost active layer depth, soil productivity, and albedo, which I mentioned earlier. There are some errors in our study that should be noted. We weren't able to use quite as many samples as we had hoped due to natural the rings sometimes disappear on junipers in certain spaces, so we weren't able to use all of our samples. So in the future, it would be good to have more samples so that we can combat that problem. Some future directions that we can go towards would be looking at August temperatures' influence on growth and verifying whether that indeed is the only summer month that is influencing the growth of the common juniper. Again, it would be good to have more sampling. It would be beneficial to study soil quality with and without the juniper and to map spread throughout the northern regions and also tracking in the southern margins. I'd like to thank Olafur Eggertsson and the Icelandic Forest Service for helping me with this work and advising me throughout the project. I'd like to thank Daniel Gavoni and Alex Tyus for providing academic advice, and I'd like to thank Hiker for allowing me to come work here and providing a wonderful space to learn and grow. Are there any questions? So there's a question about whether this work has been done elsewhere in Iceland. Not with the juniper, but there have been dendrochronology studies of birch. Yes, so there's a paper that explains, the question was about soil nutrient availability and how the juniper affects that. So there's a recent paper that was explaining how in areas with juniper, there is a certain feather moss that grows underneath that can help with nitrogen fixation. And then they found higher phosphorus levels in areas where junipers were planted, and that study was done in a tundra ecosystem. Thank you.
So thank you, Tali. Next one up is Julia Sokolowska, and she comes from Wellesley College. Welcome.
Hello, everyone. My name is Julia Sokolowska. I'm a junior at Wellesley College studying international relations and environmental studies, and today I'll be talking about my research on non-conventional vehicles as a way towards carbon neutrality here in Iceland. So the question I was looking at in my research was, what is the most fitting non-conventional vehicle for Iceland in order to achieve its climate change mitigation commitments encompassed in the Icelandic nationally determined contribution to the Paris Agreement? As a matter of introduction, I would like to speak about the Paris Agreement. It was signed 5 years ago in the French capital and is considered an outstanding and essentially a monumental triumph in the international environmental legal realm, essentially because it was signed by 197 states and later introduced in 189 of them, and noticeably the United States pulled out of that agreement as of 3 weeks ago. Why the agreement is so important is due to the fact that it aims at maintaining the global warming that's occurring at well below 2 degrees Celsius when compared to the pre-industrial levels. Something that's also unusual when you look at international legislation is the fact that there is no accountability mechanisms within the agreement itself, but it rather gives the countries the option to introduce their own ways in which they'll achieve the 2 degrees Celsius goal, which is both beneficial if the countries are committed to greenhouse gas emissions reduction. However, the countries want to, in a way, wiggle around and not really fulfill their goals. There's nothing that will prevent them from doing so. So obviously Iceland has its own nationally determined contribution. This is the Icelandic Climate Action Plan. It was introduced in the summer of 2018, and as the Paris Climate Agreement is supposed to run by 2030. The main goal of the Icelandic Climate Action Plan is reduction of greenhouse gas emissions by 35%, and that is the goal that's shared also by the European Union and Norway. And these levels that we're talking about is the 2005 levels of greenhouse gas emissions. Another very large and innovative goal that Iceland has in the plan is carbon neutrality by 2040. And the ways in which the carbon and greenhouse gas emission reduction is to be achieved is through reduction of fossil fuels use in transportation, both land and sea, and land reclamation for more marshes, as well as planting more forests, so afforestation. What I'm specifically looking at is land transportation and emission reduction in land transportation, and I'm focusing on non-conventional vehicles. So the non-conventional vehicles can be divided by internal combustion engine and electric propulsion engine vehicles, and I will be specifically looking at natural gas vehicles and the battery electric as well as hydrogen fuel cell electric vehicles. So to start with the hydrogen fuel cell electric vehicles in Iceland, Iceland is in fact the first country in the world that had a commercial hydrogen refueling station that was built in Reykjavik and opened by Shell Hydrogen back in 2003, which was closely followed by Reykjavik having 2 hydrogen-powered buses in its public buses fleet, and that lasted from 2004 to 2006. What Iceland also stands out for is the fact that all of the hydrogen, which is gas used as fuel, is produced domestically using geothermal energy, so as fuel is very clean. And something that we should look forward to in the future is the fact that there's 2 European Union projects that are currently running in Iceland, and they aim at developing and making hydrogen vehicles more accessible. And the map that we can see here is predictions to, by 2030, have 9 refueling stations all across Iceland, which, considering the range of hydrogen vehicles, would allow for traveling around the country without any sort of range anxiety. The second, and by far the most popular non-conventional vehicle in Iceland, are the battery electric vehicles. The reason for their recent gain in popularity is definitely the fact that between 2017 and 2019, there were many recharging stations built across the country, and now every municipality has a recharging point. So even though battery electric vehicles don't have the largest of ranges, usually around 200 kilometers, the fact that every municipality has a recharging station allows to travel around the country without any sort of range anxiety. The popularity of battery electric vehicles is also reflected by the new car registration rates. So March 2020 has been actually the record month when it comes to battery electric vehicles registrations, as 41% of all the newly registered cars were powered by battery electric engines. Another aspect when it comes to the future is the fact that Climate Action Plan is wanting to require of rental companies to only have battery electric vehicles, and that is important as rentals contribute 1/4 of all greenhouse gas emissions from transportation, and they also very often, usually after 2 or 3 years, sell out their cars on the local market, so that will make battery electric vehicles cheaper for Icelandic people to buy. The last type of non-conventional vehicles I'll be talking about today are the compressed natural gas vehicles. So they're by far the most well established when it comes to time history in Iceland. So first, compressed natural gas vehicles were down in Reykjavik in early 2000, and that has to do with the fact that once the landfill in Reykjavik was sealed over, there was methane gas that was seeping over, and some people decided to reclaim that gas, enrich it, and by enriching the gas, they could have the compressed natural gas to power cars and buses. That is also what Iceland stands out for, is the fact that compressed natural gas is only reclaimed, it isn't produced, which makes it much more sustainable. Similar solution was also implemented in Akureyri in 2014. So both of the cities have city buses running on CNG, as well as CNG refueling stations. The one issue with methane and compressed natural gas vehicles is the fact that methane is a finite source, and it is estimated by 2030 there will be no more methane, or not enough methane, seeping out of these two landfills. And some of the ideas that are out there is reclaiming methane from agricultural sources. The only issue that exists is the fact that it's quite expensive. In order to conclude and wrap up in relation to my question, I don't think there's one type of non-conventional vehicles that suit Iceland the most. I think it's a mix of a few. So in terms of passenger vehicles, it will be battery electric vehicles and hydrogen fuel cell electric vehicles. And for city buses, the better option will be compressed natural gas and hydrogen fuel cell. Something to really look out for is the fact that Iceland has a huge potential when it comes to creating a hydrogen economy, and even possibly exporting hydrogen gas if it is necessary, mainly in the European Union. Moreover, considering the rate at which battery electric vehicles, so zero-emission vehicles, are being implemented and bought by Icelanders, there's a huge likelihood that Iceland will in fact fulfill its land transportation commitment to the Paris Agreement. And taking that into consideration, there's a large possibility of the country achieving its carbon neutrality goal by the year 2040. Thank you very much. Any questions? Yeah. So the question was that I was talking about passenger vehicles and city buses, and I didn't mention any other types of non-conventional vehicles. The issue here is that there isn't really technology developed for any other sort of cars. There is passenger vans, so up to 9 people vans that are ran on both battery electric and hydrogen and CNG. The issue with bigger vehicles is the fact that they require more energy, and essentially engineers are still struggling with developing the technology that would allow for non-conventional vehicles that would be powered by either of the three. There's one more question? Okay. Thank you very much.
Takk fyrir, Julia. So next one up is Camille Rowe from University of Oregon.
Hi everyone, my name is Camille and I am representing the University of Oregon. Before I start, I just want to say a big thank you to Glacier Adventure and Hoiker. He has been so helpful with just all of our research and we all really appreciate it. So my project is soil health and decomposition rates at Breiðamerkjajökull. And just for a little background, increasing global temperatures have led to unprecedented glacial recession over the past century, which can be seen clearly not only around the world, but in some of Iceland's most prominent glaciers, such as Vatnajökull. And as glaciers recede, the land that's been frozen beneath the glacier for hundreds, sometimes thousands of years becomes exposed, which leaves us with the opportunity to study primary succession in the glacial foreland. Given the unprecedented rate that glaciers have been receding, we can compare differences in the foreland based on the amount of time that they've been exposed. So my study specifically took place along the eastern arm of Bredermerkyoko, adjacent to Lagoon Sarlan. And in the past 120 years alone, Bredermerkyoko's terminus has retreated around 6 kilometers, part of which was accelerated by the formation of the lagoon, which really caused an ample ice loss because of the ice calving. So this figure shows the recession of Bredermerkyoko over the past 120 years, and as you can see, this was 1945, and this is where it is as of 2016. So a pretty significant recession has taken place. For the purpose of this project, I'm going to be defining soil health in terms of the productivity of the microorganisms in the soil through means of decomposition, which will be measured through changes of dissolved oxygen. And basically, the decomposers in the soil use oxygen during decomposition, which aids them in breaking down organic matter, meaning that the higher level of dissolved oxygen, the more decomposition is taking place and the more productive the soil is. As glaciers continue to recede, their forelands serve as an ideal place to study primary succession. So with this being said, my question remains, how does soil quality differ in the foreland of Bredermerkyoko as the distance from the glacial terminus increases? And more specifically, how do decomposition rates differ in each location? So for the sake of the statistical test that I ran, I had a null hypothesis that there would be no change in decomposition rates as the distance from the terminus increased. However, I predicted that decomposition rates would increase as the distance from the terminus increased, because the longer the foreland was exposed, I assumed that there was more time for primary succession to occur. So for my methods, I had a cylindrical aluminum coring tool and 5 separate sampling sites. And from each sampling site, I took 6 cores of soil. And at each core, I recorded the coordinates to make a map later on. And all replicates of the initial sample were taken within 2 meters of the initial sample. So sample sites were approximately 300 meters apart and were labeled A, B, C, D, and E, with site A being as close to the foot of the glacier as possible, and each site after that being roughly 300 meters away. Soil samples were kept in plastic bags, which were labeled with the coordinates, sample site, and numbers. And this is a map of the sampling sites, which was made with Google Map Maker. So the satellite imagery is not up to the present date, so it looks like sites A and B are on the foot of the glacier, when in reality they're more down around here. So for the actual soil analysis, I used a handheld dissolved oxygen probe, and before testing any of the soil, I measured the dissolved oxygen that was present in the water, which was later used as a base to compare how much the dissolved oxygen had changed when it came in contact with the soil. So for each sample, I took 300 milliliters of soil and added 350 milliliters of cold water, and then immediately sealed the bag and allowed all 30 samples to sit for a total of 6 hours before testing the dissolved oxygen. And when I retested it, I swirled each bag for 1 minute just to combine the two in case they had separated. And after swirling them, I used the probe to test the dissolved oxygen, and I recorded it in an Excel file. For the data analysis, the dissolved oxygen levels at 5 different sampling sites were used to compare a one-way ANOVA with site as a factor containing 5 levels, and a box plot was created using the package ggplot2 and a Tukey's HSD was the post-HOC test used to determine specific differences between sites, which will make sense in a figure that I'll show you in a moment. So the basic results, the one-way ANOVA determined that there was at least one significant difference between sites, and the Tukey's HSD test determined that the sites D was different from sites A, B, C, and E, but the other 4 sites did not differ significantly from each other, which in short just means with the exception of one sampling site, there was no significant differences in dissolved oxygen levels from the foot of the glacier versus the sites moving away from the foot. So this was the result of the ANOVA test, and this along the x-axis is the site number, and along the y-axis is the changed amount of dissolved oxygen. So this line represents the mean, or the average, of the site's dissolved oxygen. So as you can see, there is not a huge difference between sites A, B, C, or E, but site D is significantly different with an almost 20% change in dissolved oxygen levels. Site D differed significantly from every other site, while sites A, B, C, and E showed very little change in dissolved oxygen levels, which not only rejects my null hypothesis, but also rejects my prediction that the site furthest from the terminus would have the least amount of change. I predict that this anomaly in site D was in part due to the fact that the sampling sites were in between glacial moraines, meaning that there was a lesser chance for soil to aerate and primary succession to occur. And that is just a photo I took while I was out sampling. So as you can see, it was a very rocky. So in conclusion, my data does not provide definitive evidence about the soil quality as you move away from the terminus of Bredamerkioko. There was a significant site, D, which was approximately 1,200 meters from the terminus, and there was very little difference between the other sites, meaning that soil productivity was low, which in most cases, especially in this climate, can be attributed to a number of factors such as lack of soil fertility and organic matter. And finally, this is not to say that the soil will never be productive, but only time will tell how primary succession will affect the foreland of Bredamerkioko. Thank you. And if you have any questions, let me know. Any questions? Yeah? Yeah. It was, the question was how far was the furthest sampling site from the terminus of the glacier, and it was 1,500 meters. I did not, mainly because I couldn't find enough solid evidence to make those claims of where the glacier was with confidence. So I did not measure that. Okay. Mm-hmm. Okay. Mm-hmm. Yeah, I would agree with that. That's interesting. Thank you. Thank you for your questions.
So, Camille, thank you for this. We will now step into a short break before we finish the conference. We're a little bit over halfway through. Okay, so welcome back. So next one up is Koharu Aoki from Bates University College.
Thank you. I'm Koharu Aoki, and I'm an environmental studies major at Bates College. And I know we've had a lot of natural science presentations, but I'll be doing a social studies research about exploring the perplexity of nature-based tourism in Iceland. So to set the background, I'm going to talk about the possibilities of nature-based tourism. It is considered one of the most important economic, social, cultural, and political phenomena of the 20th century. In 2017, it contributed $2.6 trillion to the global GDP, so it's a big economic boost. And nature-based tourism is a source for financing biodiversity conservation, a reason to do biodiversity conservation, and it's an economic alternative for the local people in the area. But at the same time, nature-based tourism does come with some form of consequences, environmental degradation, and that comes from like the construction and maintenance of roads, trampling of vegetations, erosions of soil, pollution from litter and vehicle exhaust. And also from our greenhouse gas emissions when we do travel to these locations and we take flights and we drive and things like that. So the carbon emissions from there. So nature-based tourism has the possibilities for conservation and for economic profit, but at the same time it can lead to environmental degradation. So in this big topic, there's this big dilemma of destroying the environment on which the success of the industry is based at. So nature-based tourism can bring economic profit and can bring conservation, but at the same time, it can also lead to degradation. So there's this big dilemma that needs to be talked about. So my research question is, how have local guide companies in Iceland balanced economic profit and wilderness conservation efforts with municipal management of nature-based touristic sites like the Vatnajökull National Park? And in order to do this, I did interview-based research. So I did 4 interviews. All of them were in-depth, conversational, informal, follow-up question-based research interviews. And they're about 30 minutes to an hour. And the interviewees were selected using a snowball method or through personal contacts. And for the ethics of the interviews, they were all asked to sign a consent form to interview and to record their interview. And so for the interviews, I did 4. I interviewed 5 people, but I had 4 interviews. One was a park manager and regional board member at the Vatnajökull National Park, and I asked them about how they manage the national park, what's their regulations, what their contracts are with the local communities. And then I was able to interview 2 local guiding companies around the area. All of them were either like founders, owners, CEO of these companies. So I asked them about what's their work ethics, what's their business model, what's their concerns, and their views on sustainability. And then my last interviewee was, I interviewed an employee of a guiding company, and this was an important part because they weren't on the board of a company or they're not representing a company. They were able to provide outside perspective and even sometimes critical perspective. So after I interviewed them, and with the recording, I transcribed the interviews and I did coding using NVivo, and NVivo is a qualitative data analysis software, and I would look through the interviews, code them, and create annotations and see correlations and differences between the different interviews and see what everyone's opinions are. So this is NVivo. I have the text on the left and my codes on the right, and I would go through each sentence of the interview and see if there's anything I can categorize in the codes, and then later I would pick on the code and see what all the 4 interviews had said about that certain topic and see any similarities or differences. In total, I had 19 codes, and this is kind of just a big word map of the codes and how they relate to each other. So one of the biggest topic was the structure of management, and this one I got mostly from the park manager. They stated that they have 4 areas in the national park, and they have their own regional board, and they have their own management plan and their own contracts. They work individually with the local community within their area, and there's a good And one thing that was interesting to find out was that this organization has a really good relationship with the local government, especially with the Ministry of Environment, because he used to be a ranger and like knows the people personally. So yeah, so they have a really good relation and they understand their intentions of wanting to conserve and protect the national park. And contracts and regulations was between the organization and the local guiding companies, and this contract was a trial run this year, and it was for them to be able to operate in the national park. And within this contract they had safety rules and environmental requirements that they have to fulfill, and they had to provide details of their business and environmental sustainability plan in order for them to be approved so that they can work in the national park. One issue that the organization wanted to look over was the issues with overcrowding. So there was a big issue with the overcrowding on the glacier. Like there's too many people on each site on a glacier. So through these regulations, they wanted to limit the number of people on each site. And however, this led for local guiding companies to not be able to bring as many clients as they would be able to. So this limited their company's ability to do their business and limited their growth. And there was some unhappy response from guiding companies. But they also still understand the value of their regulations and understand why they need to limit the number of people. And for the sustainability and what the local guiding companies are doing, they talked a lot about carbon offsetting and afforestation. And the most popular topic among 4 of my interviews was about vehicles. We talked a lot about electric vehicles, carpooling, and super jeeps, as they're all guiding companies. You need these big, massive trucks, cars to get to the foot of the glacier. But one interesting aspect we talked about was from the employee about helicopter tours and why some companies choose to do helicopter tours, some companies won't choose to do helicopter tours, and if these companies are actually thinking of their greenhouse gas emissions from these helicopter tours, or are they just thinking for profit? That's still a dilemma that needs to be explored. But so for notions for businesses to use electric vehicles, which a lot of the companies I interviewed has electric vehicles, are they doing it because they're considering of the environment, or is it because electricity is cheap in Iceland? So what's their intentions and why are they doing that? That dilemma still needs to be explored. But at the same time, sustainable development does consider the environment, but also the economy, the sustainable development of the company itself. So is using electric vehicles considering both factors. But another thing from my interviews that I thought was really important was highlighting the fact that Iceland itself is a very green society. It's very green at its core. The size of the population, location, how close we are to the glacier, and how accessible that is. You don't need to drive that far to get to the foot of the glacier. Or the energy, like the cheap accessibility to green energy like geothermal and hydro, how that has affected how Iceland does sustainability. So for my conclusion, at the end of the day, financial incentive is indeed a big factor in decision making, especially in our world today, in terms of like cars and carpooling and stuff like that. But we also need to consider how green Iceland is and how the geography of Iceland have made it easier for businesses to be green. So being green in Iceland can be cheap, especially with the use of energy and electricity for their cars. And cheap and easy goes hand in hand in Iceland. And Iceland is unique in its ability to financially incentivize to be green, which is a very rare case. And I think Iceland is a very unique case study in terms of that. And on top of that, management of the national park and their relationship with the government has made conservation efforts in the national park very smooth. And that's also another rare thing compared to other countries. So I concluded that it's easier to create a sustainable, in terms of the economy and environment, it's easier to create a sustainable business in Iceland, especially for nature-based tourism. Thank you. Any questions? So the question, yeah. Mhm. Okay. So the question was, what are the contrasting opinions between the guiding companies and the national park? Um, I think the biggest was about the issues with overcrowding. They were limiting, so the organization wanted to limit the number of people that could go on each glacier every single day. And a lot of companies would apply seats every day and be like, I want 300 seats, I want 20 seats. But a lot of the companies didn't get what they wanted because they just apply for too many, or they were just limiting as much as possible. So because they couldn't bring as many tourists to their destination, they were really unhappy about that. And one thing that they didn't mention was that they were doing this, they were limiting the number 650 people, but they weren't doing it based off of a specific scientific result, like 650 is the capacity. They haven't done that research yet. So one thing one of the guiding companies mentioned was that they were hoping they would choose this number out of research, not just out of nowhere. So then they would be more justified into regulating the number of people. But at the same time, the organization did say that they're conducting research on the limitations this winter. So I think the number could change. It could go up or it could go down, but the guiding companies want some sort of scientific reasoning behind that number. So that's one thing that I think had the biggest difference between the two. Thank you.
Thank you, Koharu. So next one up is Davy Henry from Bate College. Welcome, Davy.
G'dayan. My name is Davy Henry. I am a third-year geology major at Bates College in Maine. During my 5-week research project, I looked at numerical glacier system modeling. For some background, I feel like, as we all know, being here in southeast Iceland, right at the base of Vatnajökull, glaciers are melting at a rapid rate. This is due to an increase in global warming as we put out more carbon dioxide into our atmosphere. There's an increase in temperature of our Earth's planet, and this has detrimental effects, like this has detrimental effects on the rest of the Earth. However, glaciers have many important functions. This includes having a high albedo and also being an integral part to the water cycle. Detrimental effects include sea level rise, which can potentially put a lot of cities and land across the globe underwater. This can also lead to collapses of ecosystems and changes in ecosystem regimes. For my research, I wanted to analyze where glacier systems are stable and non-stable by analyzing their equilibrium points of their system's phase portrait, which I'll get into later. For my methodology, I wanted to create a model using Python, which I'm nearly done so I will not be showing you that data today, but I thought I would explain to you the setup of my system and the equations I used. So first I had to define the system using ODEs, which are ordinary differential equations. I used, which show the rate of change of a quantity within time. So I decided to look at volume and length, which are two ways to look at mass balance within glacial systems. And my equations I used were manipulated from Johannes Orlemans. So essentially what I've done was to solve this double integration of the three-dimensional glacier by using initial conditions, a time-step series, and then finally solving it using Euler's method. So the figure in the top right-hand corner kind of gives a visual representation of the mathematical theory of like the double integration. So you have a three-dimensional shape, and by taking small sections, by using small sections within the x and y dimension, you can solve the area under the curve, and then it will give you volume and length. For potential space is a good way to like understand phase portraits, what I will be outputting within my model. So if you think about potential space as hills and valleys, and the hills are transitioning between one state to another, where valleys are areas of stability and hills are regions of instability, and with a slight noise or slight perturbation within the system could displace the ball, which is showing where the system is at that moment. So if we apply this to the phase portrait, it's pretty much the same thing, but the equilibrium points are where the system crosses zero, meaning there is no change within time. And this translates to the hill or valleys, where the slope of the curve is going negative, is the valleys where you have stable points, and then an increasing slope shows unstable points. So what I think my model will show is something similar to this, where one stable equilibrium point would be a no ice and no glacier, which would signify, which goes along with the theory of like no change happening within the system. And then another stable equilibrium point is where the glacier accumulation zone is 2/3 of the ice or ice cap, and then the ablation zone is 1/3 of the glacier. And then our unstable equilibrium would be anything within that, as it's trying to move into one stable point or another. Another really interesting idea that this poses is the idea of critical slowing down. In the mathematical world, this is saddle node bifurcation. So pretty much if you think this ball is pretty much on a pendulum, and as you push, or if you push on the pendulum or create more noise with that, it's going to take longer and longer for the pendulum to come back to its original position. So these fluctuations, as it nearing its tipping point, you might think things are slowing down, but however, it could lead to a very abrupt change, which is something we may be seeing. In conclusion, even though that I created a very simplistic model that doesn't have precipitation, albedo, or any like resilience factors within the system, a simplistic model like this can show the interworkings of the glacier system that you may miss within other models. And this can also help further understanding of conditions of a stable glacier and where we are and how we fit into that track and how climate change is affecting all of this. Any questions? Yeah, the question was having a lot of abstract like math behind all of this, and how being out in the real world affects how my research was done. Yeah, definitely. I think it's interesting with this, where are we, like, within the model? Like, have we hit the tipping point yet? Like, if you look out or take a tour or go out to Breidmeriørjökull, and where you go to the parking lot, that's 2010. And you can see the difference between that amount of recession and then how you can see the last moraine there. It's like all used to go to the entire highway. So I think a really interesting question with this poses is that, have we already hit the tipping point? Are we no longer experiencing this critical slowing down because and it can return back to that stable equilibrium of having the correct amount of accumulation oblation? It's really interesting, and being out in the field and stuff has really developed more like what this means within glaciers, within the larger system of our climate. Yeah.
Thank you so much, Davey. So next one is Raven Dawson from Charlton College.
Hello, I'm Raven Dawson, and I'm going to be talking about the insulative properties of moss in Iceland, more specifically in southwest Iceland. So you've heard before in some of the other presentations about climate change. It's going to have some major impacts and shifts in the environment around us, from more extreme weather events to changes in what is considered a normal year. One of the main drivers for climate change is carbon dioxide in the atmosphere. There's many solutions to reducing this. You can reduce it both in the production of carbon dioxide into the atmosphere, or you can try to extract it out of the atmosphere. One way they're trying to do that is large-scale tree and forest planting. The trees absorb the carbon dioxide and sequester it in the biomass of the trees themselves, and this removes it from the atmosphere in a harmful form. One of the problems with this is that as climate change gets worse, you have more extreme weather events which damage young trees more than they damage the older trees. This makes afforestation or refreshing forest spread much harder to do. So you need to add protections to increase the survivability of young trees. Both can be done naturally or through man-made protection, such as tarping young trees. I am looking at moss and seeing if you could use moss as a protection to help these young trees increase their chance of survival. My goal specifically is to determine whether the moss has insulative properties and it would be therefore useful in preventing freezes earlier in the season from killing the young trees. To do this, I had 40 field sites set up in Mosgilsá, Iceland. This is just north of Reykjavik. 20 field sites set up in red here. They are in the meadow environment, and I had 20 set up in blue. They are in forest. That's a single species stand of lodgepole pine. For sampling, we had 3 different types of moss cover. We had high, low, and medium moss cover. High moss cover is shown in figure A and B, with over 90% moss cover. And C and D is low moss cover, under 10%. All percentages were done with visual estimation. Each plot was sampled for multiple days to get enough data, and they were sampled in the morning. This was when temperatures were most stable, and therefore it would give us a clear picture. Samples were taken of surface, temperature, soil depth, at 5 centimeters and a soil temperature at 10 centimeters. Moving on to the results. You are looking at all the samples. This is both from the meadow and the forest. And on the y-axis, that's difference in temperature. That's the difference in the temperature from the surface to our soil temperature. So one way to look at this is the larger the difference, the warmer the soil is compared to the surface temperature. So we can see across both different depths that high moss cover kept the soil much warmer than low moss cover. And this was a significant difference for both of them. Medium moss cover was not significant for either high or low. Again, now just looking at the meadow environment specifically, we see the same trend happening with high moss being significantly different than low moss and keeping the soil much warmer. Moving on to the forest. We still see the same trend with high moss being significantly different than low moss, but we're now also seeing high moss being significantly different than medium moss. This was slightly different than the meadow, and so I wanted to look into these relationships and see if something more complicated was going on. So here we're looking at the meadow environment in gray and the forest in orange, comparing the different depths and temperatures at each of these depths. As we can see across all different types of moss cover and both different depths, our meadow environment kept a much warmer soil temperature compared to our surface temperature than the forest did. I'm not fully sure why this is the case. One possible explanation for this is that the meadow had grass and other vegetation growing along the bottom, whereas in the forest there was moss, but without the moss it was a pine needle bed, which may have less insulation than the vegetation in the meadow. Some of the conclusions: because we saw across both environments, meadow and the forest, along with together, that high moss concentration had a much larger difference in soil temperature than low moss concentration, it seems safe to say that the moss is insulative on a small scale, and that therefore it would be useful to protect young trees and saplings. One issue with this: all sampling was done in the fall, where the surface temperature was colder than the soil temperature, and so the moss kept the soil warmer. In the spring, you would have the opposite effect, where the moss would be keeping the ground frozen longer than the soil around it. So if you were planting in the spring, this may cause problems, and you'd want to check under moss to make sure that it has thawed. Overall, moss seems to be a useful way to protect young trees for afforestation or replanting of forests, and it would be useful. I would like to thank the Icelandic Forest Service for both providing me with sample locations and advice. I would like to thank Hiker and Glacier Adventure for providing us with this wonderful space to both hold the presentation and to work. And I'd like to thank Dan, one of my advisors, for statistical help. Thank you. Any questions? Yes.
Yeah, well, thank you very much. I'm thinking about this anomalies today that you mentioned with the forest, that the impact of the pine needles, I think that would be quite
Yeah, so the question was, because of the species I chose, lodgepole pine, the needles are acidic and will kill off lower vegetation, so it would be interesting to look at a birch forest which is native here and see the effects there. And yeah, I would have liked to. The place I was looking at, unfortunately, it turns out it's very hard to find low moss areas in the birch forest. The moss cover was pretty continuous out throughout the birch, at least at the area I was looking at. So it was going to be my first choice, but the sites were just not there for me to study.
Thank you, Raven. We're almost on time, yeah? 5 minutes past. So now we're going to make a very, very short minute break to be able to set up a camera for the last presentation. Thank you for being with us and being so patient. Okay, welcome back. So next one up is Nicholas Beck and Friends from Whittier College, and he's going to show us a video presentation. So Nick, take it away.
Hey, thank you, Hoiker. Hello, my name is Nicholas Bach and French. I am an undergraduate studying environmental science and policy with a minor in glaciology at Whittier College in California. I'm honored to be here today, and I'd like to thank Hoiker for organizing and hosting this event. None of us would be here conducting our research at this beautiful place without him. In the past few years, I've become fascinated with the grandeur and beauty of glaciers, and also what they can tell us about our changing planet. So naturally, I was drawn here to Iceland, and upon arrival, I quickly came to realize the immense impacts that glaciers are having here in Iceland. As I began my research and exploration, I discovered the incredible changes occurring to the landscape, specifically the proglacial lakes expanding as the outlet glaciers of southeast Vatnajökull recede. I was captivated and immediately set out to document these glaciers and their respective lakes. Glaciers are unique such that their changes can be observed on a human timescale. And as researchers, I believe it is important for us to be able to communicate our findings to the public, especially on matters of such great public concern such as climate change. So with this project, that's what I set out to do, to visualize the changes happening to the ice. Before I begin, I'd like to thank Thorviður Andersson and Kieran Baxter for advising and guiding me through the project, and whose upcoming film, After Ice, provided the main inspiration for my film. Without further ado, ice to water. Thank you. Thank you. All right, I think I have a minute for questions. Yeah. Definitely. Yeah, so the question comment was just about adding in the kilometers of retreat that the glaciers melted away. I think when I was approaching this film, I think I was looking at like the expansion of the lakes, but of course that's also tied to the ice, so that could be good information to put in as well. I appreciate that. Thank you. Okay. All right. Thank you very much.
Yeah, or you can have it. That's okay.
Okay.
So thank you, Nick, for this. Yes, we're going to check if we got some questions from YouTube channel. Okay, so then this is almost to the end, and I would like to ask Dr. Þorvarður to comment, sort of finish of the conference.
Thank you, Haukur Ingi. I'm just going to take this off, but it's a reminder of what sort of predicament we find ourselves in today. And terrible as the COVID-19 pandemic is and has been, it's also created spaces for new things, and such as we've been witnessing today. And this has actually been an incidence of multiple serendipity. The fact that Haukur Ingi and Berglind had this dream of developing these buildings that have now were unused for their business and for their own aspirations in education and tourism and other things. That we had this fantastic group of international students coming to Iceland during the pandemic, a crazy idea, I don't know how you... And then the very fortuitous meeting of Nick and Haukur Ingi, which led to this fantastic group of students coming here to Suðursveit, to the Hali or Breiðabólstaðir farms. So wonderful things happen. I think that's something to remember in all of this gloom, doom and gloom of COVID-19. For me personally, this has been like Christmas coming early. I happen to be a very interdisciplinary scholar, and therefore I enjoy very much all sorts of different kinds of scientific and scholarly information and thinking. And so that was one huge gift to me. But also I was very inspired just to listen to this large group, interdisciplinary group of young people talking about this area primarily that I've lived in for the last 15 years and have become very deeply attached to, and not in the least the glaciers. So that's another reminder to us that climate change is not only a global issue, it's humongously global. Because climate change, the nature of this problem is such that it affects basically everything. Most things over a relatively short period of time, but there are certain exceptions, such as glaciers, where we can see the reality of the climate change during our short lifespan as human beings. And this, so glacier melting, it's not just about the glaciers, it's about everything else that's happening to our world because of catastrophic global warming. And therefore we need to use what we know about glacier melting basically as a wake-up call to start noticing the other effects that are happening more slowly or are happening in fields or to organisms or whatever that just haven't been studied in this regard. So it's also so wonderful to see the effects of climate change being studied with regard to junipers and moss and all of that, those things. So it's been an absolutely wonderful day. And yeah, the point was also I wanted to mention that because it's such a huge, humongous global problem, the only way that we can really address climate change is to do so together from multiple perspectives of all possible sciences. But we also have to remember that this science, it needs to connect to the normal world, to use Haukur-Ingi's term. We can also ask what has happened for the science world to become distanced or even disenchanted with the normal world, and how we can repair this bond, this vital bond between science and normal citizens or regular citizens. So I'm not going to say much more. I could talk a lot. My hope in the young people of the world has been very, very strongly affirmed today. We place our hope in you. And just so that I get the names correct, yes, we place our hope in you. Owen, Celine, Laila, Talia, Julia, Camille, Aoki, Devi, Raymond, and Nick. And we are going to be there to back you up, just so you know that. So from our part, I want to thank our hosts, Haukur-Ingi and Berglind, very much for this opportunity and for their strong support to this. And yeah, see you guys again. Thanks.